Here we saw Poisson's equation. So viscosity, this is the concept. Viscosity, first you have Newton's equation, then you have Poisson's equation, then you have Stokes law. In the Stokes law only you have the terminal velocity. Most of the time they ask questions from this because most of them find this like confusing. Terminal velocity thing, they find that as confusing, so most of the time this is the thing that they ask. Okay, we'll look at that, the most important part of viscosity. What did Stokes say? Stokes law, no? So Stokes, what did he say? He told, when a solid sphere, what sphere? Solid sphere, this is only for spheres, moves in a fluid, the layers of fluid, now if you take consider a solid fluid, and if this is moving with velocity v in this direction, there are layers of fluid now. The layers of a fluid in contact, now the fluid they represent here is the viscous fluid. So viscous fluid, the layers of the fluid in contact with the sphere will move with the same velocity v. Meanwhile, the other layers will be at rest. So there is a velocity gradient, delta d. Delta d, v d. V, this is 0, so there is a velocity gradient across this. So how will that be? Something like this. The d move out, d, and this will be at rest. That's how the velocity gradient will be. Okay. So he gave an equation for the force. He directly gave it, 6 pi r eta v. This is the equation that he gave. Okay, why did he give this? Because now you already know when two these plates are there, if one is sliding on top of the other, if this is rest, there will be a frictional force. Same concept here, this is at rest, so this will apply a frictional force for this layer will apply frictional force for this layer, because this is faster than this will apply there's an overall viscous force acting in the opposite direction of the motion. Viscous force is a frictional force, no? So that should obviously act in the opposite direction. So this is acting on the opposite direction. Okay, so he is saying when a solid sphere is moving in a viscous liquid, the layers of the liquid in contact with the sphere moves with it, meanwhile the other layers are at rest. So there is a velocity gradient created between this layer and the other layer next to it. Okay, so there is a viscous force that is created and it is opposing the direction of motion of the sphere. Okay, and he gave this equation and he told, this is the force, viscous force on a spherical body, this is the coefficient of viscosity, this is the radius of the sphere, and this is the velocity with which it will move. Now in exams, in the MCQs, they might ask, in the MCQs sometimes, or in the essays sometimes, they might ask you to prove this dimensionally correct. So you can prove that using units and dimensions knowledge. Okay. Now this is like a beautiful story. Okay. Now consider a situation where a solid sphere is dropped from rest. This is a liquid, sphere is there, u equals 0, it is dropped from rest, okay, into a container with infinite height of the liquid container. What do they mean by that? This one is not reaching the bottom reach panadilla, there is no bottom, infinite height. Okay, that is what they mean. So as soon as the ball falls into this thing, how can I say, the velocity of the sphere will be 0, u equals 0. What are the forces acting? The weight will be there, w, and upthrust will be there. Now you might argue with me saying that this is a viscous liquid, so viscous force should be there. How can viscous force be there? I told you u equals 0. If according to this equation, if this is 0, how can this be there? This can't be there. So viscous force is 0. So these are the two forces. So u equals 0, therefore F is equal to 0. If you have the knowledge of waves, you can remember even in simple harmonic motion, when there's acceleration maximum, at that moment velocity is zero. That is v min. When v max, it is a min. Maximum velocity will have zero acceleration. That's why a equals minus omega squared x. In the mean position, there's maximum velocity. In the corners, there's maximum acceleration. Why is there no acceleration? With this equation itself you can prove. Why x is 0, no, in the mean position. So this should be 0. With that itself you can prove. Okay. So acceleration will be maximum initially. Okay. No force because velocity is 0. Because velocity is 0, there's maximum acceleration in the beginning. When soon as the ball is dropped into a liquid. Okay. Now we'll consider the next situation. Now before considering the next situation, you can apply sigma f upwards equals sigma f downwards. So sigma f upwards is equal to u, sigma f downwards is equal to m g. Sorry, my bad, you can't apply this, I forgot. Why you can't apply this? This is not an equilibrium, no, there is a maximum acceleration, you can't apply this. Yeah, so what you do, you apply f equals ma. How do you apply? You applied f equals ma downwards. Why did I choose this? For this direction to be chosen, I chose the weight of the solid sphere to be greater than upthrust. If this downward force is greater than upthrust, only no, the ball will go down. That's why I consider this condition. This is the condition. Okay, so mg minus u equals m acceleration a max in this condition. So with this, I might ask you a question. As soon as you drop the ball, what will be the acceleration? Something they will ask you. You have to find. Okay. Now, so we told the condition. This is the important condition. This thing is moving downwards when the weight is greater than the upthrust. Now, acceleration is there, no? So object should start to move, no? So when the object starts to move downwards, the velocity is not equal to 0 now. At time t equals 0, it is 0. But now if time is t equals to t, velocity is not 0. Why? There is an acceleration. If there is an acceleration, in the next second there should be a certain velocity. So if velocity is v, the force should be viscous force. Now this is mg, upthrust is there, and there is a certain force. Why? This v is not 0 now. V is not 0. So that force is 6 pi r eta v. Okay. This is the viscous force. So if you apply F, and still the motion is downwards. Still the motion is downwards. Now velocity is not 0, no. So acceleration is not a max. Acceleration is decreasing. This is a famous MCQ point. When a solid sphere is dropped into the liquid, until it reaches terminal velocity, acceleration is not constant. Acceleration is varying. Acceleration will decrease from a max to 0. Velocity will increase from 0 to Vmax. Vmax is terminal velocity, we name it as V naught. This is the terminal velocity. The force exerted on the terminal velocity is the maximum viscous force. Okay, we'll come to that in the later part. So if you apply F equals ma downwards, you have mg minus u minus f. This f is also acting upwards, no? Minus f is equal to m. Okay, this is the other part. Now what's happening? Now I told you velocity is not 0 now. There's acceleration now. So viscous force is slowly increasing when going downwards. So the viscous force also should increase when going downwards now. Acceleration should decrease when going downwards. So if acceleration is decreasing, viscous force is increasing, what can you say from this equation itself? There will be a certain point where the ball will be at equilibrium. Okay, so at equilibrium acceleration will be 0. If acceleration is 0, I told you over here, velocity will be maximum, max. What is Vmax? I wrote it here. Here Vmax is V naught. This is the terminal velocity. So So acceleration is 0, upthrust and viscous force, if this is 0, mg will be equal to u plus f. Upthrust and viscous force will balance the weight of the object, so there is no resultant force, so this is in equilibrium. Now v naught will not increase further, v naught is constant, right? So this is called terminal velocity, when the velocity of the sphere is not increasing and it is constant value, that value we call it as terminal velocity v naught. Okay, okay. So this f will be equal to 6 pi r eta v naught, v naught. Okay, remember that. Now we'll go for the graphs. When you consider the graphs, you have vt graph. Vt, what is this? Terminal velocity. How does terminal velocity vary? Now think, okay? Before you remember this and memorize this graph, you should think about the graph. Then only if they alter the question, you can alter the graph knowledge, because even when they might alter the question in such a way that you not get this typical graph, you might get another graph, because they might drop it from a certain height and they will give you the option of this graph also. So you might quickly see, okay, I memorize this graph, and you might put the answer for this graph. But if you understand the concept, then okay, you will think, okay, this is not the graph, there is something else happening, so there should be a modification of this graph, and you will do the question very well. That's what I'm saying, think. Now initially, at time t equals 0, what I told, at time t equals 0, u equals 0, so the velocity is 0, so it's starting from 0. And I told you acceleration is constantly, not constantly, acceleration is decreasing, so velocity should increase. But how is it increasing? It is increasing in such a way that the velocity, that's another point. Now when you consider vt graphs, if you say acceleration, this is vt, acceleration is this now. But what if there was something called increasing acceleration? If it is increasing acceleration, the velocity time graph will be like this. What if there was decreasing acceleration? Decreasing acceleration, the velocity will be like this. Similarly, increasing deceleration like this, decreasing deceleration like this. Okay, these ones you learn it in linear motion. Okay, and jerk and on decay, that is also there. Okay, so now acceleration is decreasing, so decreasing acceleration, this is the graph. So if we divide the, and it will be constant, this constant value is v naught, terminal velocity. That's all. This is the terminal velocity graph. Now what about acceleration? What I told, acceleration is initially at a max when t equals 0, acceleration, and then it's coming. Now when you collinearly locate these two graphs, when this is the maximum velocity, terminal velocity, this acceleration should end at 0 over here. It goes like this. It's a curve. Why is it a curve? The acceleration is constantly not reducing. It's decreasing in a decreasing manner. Decreasing in a decreasing manner. That's why this is also a curve. This is the acceleration versus time graph. This is the velocity versus time graph. This is the maximum acceleration when the object is dropped, as soon as the object is dropped into the liquid, a max. So t equals 0 a max. And when it is reaching the terminal velocity, acceleration should be 0. Why? Terminal velocity is the maximum velocity. And after that, the velocity will be constant. At this point, this is the equation. 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 You should remember that. Okay. Now, with all those said and done, we'll move for the equation of V naught. This is not a big thing, but some fellows, they struggle with this. Okay. Now, if you take an object in a liquid of density rho, this one's density is sigma. Okay, this is the solid sphere. Because for solid spheres only you can apply Stokes law, then they only you have terminal velocity. Okay, and this one's radius is simple r. Okay, what can you say? F max F max means maximum viscous force. Maximum viscous force at 6 pi r eta v naught. Terminal velocity. You have maximum viscous force. And in the previous page, okay, I'll show you. So when F is F max, you can apply only this equilibrium concept. So mg plus u equals F max. Sorry, my bad. Mg equals F plus u. F max plus u. Okay, because this is downward force, this is upward force. Sigma F downwards, sigma F upwards. Research student. Okay, so yeah, mg is equal to F max plus upthrust. So and this is fully immersed, no? So what can you say? A mass is equal to m is equal to v rho, right? Not rho, here it's sigma, v sigma. So v sigma g will be equal to 6 pi r eta v naught plus, now upthrust is what? Volume of the object displaced in the liquid. So here immersed in the liquid. So the whole volume is immersed, right? So I put v, and the density of liquid is rho g. This is the equation. Now what is the volume of the sphere? Okay, wait, before that you subject the terminal velocity value. 6 pi r eta v naught is equal to v times sigma minus rho times g. Okay, like this. Now you further, okay, you keep it like this. Now what can you say about the volume of the sphere? Volume of the sphere is 4 over 3 pi r cube, right? Sigma minus rho g, okay, sigma minus rho and g. Here 6 pi r eta v naught. In pi and pi can get cancelled, 1 r can get cancelled, here r squared, this will get 3, this will be 2, and when you subject v naught will be 2 over 9 eta sigma minus rho times g. This is the so-called terminal velocity equation. My bad. You can see my simplification. I forgot to check the camera. Okay. So this is the so-called terminal velocity equation, which the fellow struggled to memorize. Why do you even need to memorize when you can find out? Simply equate the forces downwards and upwards at equilibrium and then put, and you can find this terminal velocity. Because if you don't know physics, if you don't know the concept, and if you are relying only on this, you just take the equation worksheet and if you memorize this, and in the exam you forgot what is there in between. Rho minus sigma, that is sigma minus rho, sigma da the density, the density, you forget. Why do you even struggle like that? If you know the concept, just apply this, you will pass it, you will get this equation. No? You don't need to struggle also. Okay, this is the terminal velocity equation. After that, we have the conditions. Important thing, I forgot about this. Conditions to apply Stokes law. What is the condition? These conditions are like super important. Okay, when you compare Poisson's equation conditions and these conditions are very much important. What is the first thing? The fluid should be at rest. That means when you drop this ball, this liquid should be at rest. Okay. Second, fluid should be infinite extent. I told you, infinity height. Or else if this one is very much dense, this one will easily go and hit the bottom. No, if there is no bottom, it will continue going. That is where you can apply the Stokes equation. Okay, Stokes law. Okay, and third thing, if simple r is the radius of the sphere and capital R is the radius of vessel radius, capital R should be substantially larger than simple r. Okay, why is this? Then only you can, if this is very much great, only you can say that the corner, when the ball is like this, if this is the walls, then only you can say this is velocity is 0 and this one's velocity is with v. If this is narrow, how can you guarantee that this one is at rest like this? That's why they are saying this should be larger than this. For this to be large, for this distance to be larger, the radius should be large enough. If this is a vessel, The radius is large, only know this one will be u equals 0. If the radius is small like this, how can you say this is 0? That's what they are saying. That is the third condition. So what is the first condition? Fluid should be at rest. Second condition, infinite height. Third condition, substantially the radius of the vessel should be greater than the radius of the sphere. Okay. The fourth condition is sphere should be released from rest. That means initially when if you consider this, as soon as the sphere enters the liquid, the fluid should be at rest. Then only now you can say initially the weight and upthrust is only there and there's maximum acceleration. If there's this, then terminal velocity will if there's this, there's a velocity, so viscous force in the beginning itself will act. No, then you can't put that condition. That's why over here I told you the first condition, second condition, Kira. That only this. So sphere should be released from rest. That is the fourth condition. What is the fifth condition? This fluid, the sphere, should be released along the axis of the vessel. If you consider this as the vessel, along the axis of the vessel only the sphere should be released. Okay. And the sixth one, the region which is used in the measurement of the terminal velocity should be far from the bottom of the vessel. That means if you consider this as the vessel, if this is going like this with infinity, if the sphere is dropped here and here is the terminal velocity position, this one should be very much greater. This one should be very much greater. That's what they are saying. The region which is used to measure the terminal velocity, okay, should be very far from the bottom of the vessel. Should be very far from the bottom of the vessel. The region where you measure the terminal velocity should be very far from the bottom of the vessel. Okay, these are the conditions. Now what is the first condition? The fluid should be at rest. Second condition, fluid should have infinite extent, infinite height downwards. Third, the radius of the vessel should be substantially greater than the radius of the sphere. Fourth, the sphere should be released from rest. Fifth, the sphere should be released along the axis of the vessel. Sixth, the region where we measure the terminal velocity and the bottom of the vessel, there should be a very far distance. It should be very far. Okay. So these are the 6 conditions. These are the conditions for Stokes' law. So what are the conditions for Poisson's equation? Recall. The liquid should be streamlined laminar flow. How can you get this? By lowering the pressure difference across the tube. And second one, it should be steady flow. Third one, the liquid should be incompressible. Why it should be incompressible? Then only this one won't change. If it is incompressible, this one will change. Then you can apply the Poisson's equation. Then the last one, the tube in which the liquid flows through should be horizontal and narrow. This is all viscosity. So you can slowly try the Peirce rule and slowly move on to the, I don't think you need essays this time, because but to understand the concept you need essays only. But now, as you don't have much time, it's better if you just go on with the MCQs. And if you can't understand certain MCQs, you can drop me a text. I can inshallah sort it out for you. Okay, there are many interesting questions with regarding to terminal velocity, Stokes' law. Okay, always remember, viscous force is a frictional force. If there is motion in positive x direction, viscous force will act in the negative x direction. For the sphere in the viscous liquid, it is Stokes' law. For a certain object sliding along oil, that is the Newton's equation. For a tube in which the liquid is flowing, for that Poisson's equation. Only 3 things in viscosity. Now peacefully you can do the viscosity questions. See you in the next video. Bye. Assalamu alaikum.